Hello ladies and gentlemen, let's go through this example here. And what we have are a couple of signals that V1 is this, and it's the green waveform on this plot. I like to make a sketch, a plot of things so I know what's going on. V2 is the blue. Comparing the maximum of these two, the maximum is at 30 degrees here for V1. The maximum is 150 for V2. So that means that the phase angle is going to be 120 degrees. That's going to be our final answer. I want to just label the origin just to make sure you guys know where it's at. Okay, let's take a look at how we analyze this. First of all, it drives us a little crazy. The radians and degrees can drive us a little crazy because omega is 1,000 radians per second. And I made a mistake on my chart and forgot to label it in degrees instead of radians, so I'm changing that right now. So what we have is a unit of radians here and then degrees here. And we just got to remember that. And just remember this is pi over 3 radians. And this is pi over 6 radians. And that's what they're trying to talk about. First of all, we want to find the frequency. There are 2 pi radians per 360 degrees. So this is going from 0 to 360. 2 pi radians. And that's how we can use our conversion factor to get frequency. Not angular frequency. This is angular frequency. F is regular frequency. So 2 pi radians, there's that 2 pi right here. 2 pi radians per 360 degrees. Okay. Moving on. To look at this thing mathematically. Now I've already done it by drawing a picture right here. We want to do it mathematically now. We got to express both as positive sine or positive cosine. And right here we have a sine, we're comparing it to negative cosine. So we need to fix one of them. We'll take care of the negative sign. We talked about our trig identities, that you can convert the negative to positive by doing this, adding or subtracting 180 degrees to the angle with this identity. So we convert the right hand side of the equation. The only difference here, well, we've dropped the negative sign and we've added 180 degrees. We probably should have subtracted because the next, doesn't matter. We'll move on. Now, we're going to take the left-hand side and make the sine into a cosine. So sine of an angle plus 90 is the cosine. Or we can do it vice versa. So converting the cosine into a sine. So we're converting this into a sine. We take the angle given before, which came from this equation right here, and add 90. The cosine equals the sine of the argument plus 90. That's the trig identity. Now, this gives us 210 plus 90 is 300. That's a little big. We want to convert it to negative 60 because we want to be working. The convention is, for when we're talking about this stuff, people don't like to work between negative 360 and positive 360. This graph, I did it. but they want to work in this range here. Negative 180 to positive 180 degrees. So remember that we can subtract 300. This is where we can subtract the 360 degrees. The sine of theta is equal to the sine of theta minus 360 degrees. And does that make sense? Yes, it does. Take a look. We're considering V2, the blue line right here. Here's the origin. It looks like it lags, so that means there'd be a negative 60 degrees by 60 degrees. The distance between here and here looks like it's 60 degrees on the chart. So it makes sense. We're taking away 360 from this. Okay, so now we have V1 and V2. They're both the same function and positives. And we can compare the phase angle between the two. Well, V1 is already positive 60 degrees. Does that make sense? Here is the green is V1 and it's positive 60 degrees. It starts here. V2 starts here. Or you can look at the maximums, which I did at the very beginning, and see that the phase difference between the two is 120. Who lags and who leads? It looks like V1 leads and V2 lags. That's all, folks, for this example. Now, I want you guys to do this one right here. So pause, work on it on your own as practice.